All right, welcome everybody. So our speaker today is Asaf Shachar. He's from the Hebrew University of Jerusalem, and he will talk about incompatible elasticity, embedding surfaces with minimal distortion. Thanks a lot for coming, and please go ahead.
Okay, just a second. Yeah. So thank you very much for inviting me. I'm happy to be here. Yeah. Okay. So let's start. Just a second. So, yeah. Yeah. Okay. So let's start with. I will start with some a very brief review of some model of standard classic elasticity theory. So elasticity theory is, in a sense, mathematical theory which tries to model and analyze the behavior of elastic bodies. So what is an elastic body in our model? In this model, an elastic body is just a domain in RD, where D is usually 2 or 3. Let's think for a moment of some bulk object, like, I don't know, a full ball in R3 or something. And this domain, we think of it as the reference configuration of the body. Okay, so the body comes it's a subset of Euclidean space, and in other words, it comes with equivalently, it comes with a preferred embedding inside Euclidean space, where the dimension of the body. So when I'm talking about a domain, I mean, let's say a compact something which is in 3-dimensional, let's say a 3-dimensional compact manifold, a 3-dimensional open subset of R3 with a boundary of certain regularity. Okay, so this is what you need to imagine. And an elastic energy is a function on the space of configurations, where a configuration is just a mapping of omega from our body omega into RD of a certain regularity, which I do not specify exactly what, but this is of course needs to be specified in the model. So just a mapping of some regularity, let's say leaf sheets or some solar space or something. And the energy, as I said, it's a function on the space of configuration, so it's a functional, which is given by an integral. So it's an aggregation of local distortions. So it's an integral over omega of some energy density W, which measures the local distortion of the map. And a prototypical energy density is just take the distance W of a matrix A, just take the distance of this matrix from the group of rotation matrices from SOD and raise it to some power. Okay, so this is a prototypical example of an energy density. And in this framework, the elastic problem is to find energy minimizing configurations under constraints. And the constraints here is important, of course, because, I mean, if I do not put any constraint, I can just take the inclusion map, right? The identity map from omega into RD. It will be an isometric immersion. It will have 0 energy, right? So it's a trivial problem. But once I'm putting non-trivial constraints, let's say on the boundary values of the map or other kinds of constraints, I'm getting a non-trivial problem. So this is classic elasticity from a certain perspective, anyway. And it turns out that sometimes this model is insufficient to describe various kinds of natural phenomena occurring in nature. So here's an example where you do not have a configuration without distortion. So this is a real carrot, which actually my colleague Simar cut it in his kitchen. And after the carrot has been cut, you can see that it has been deformed. Okay, so and this deformation that the two parts got means that this carrot wasn't entirely happy before. I mean, before we cut it, it had some internal stresses. It had some internal stress, and after we cut it, it used, in some sense, the additional degree of freedom it now has. It now got to release energy. So we cut it. There is additional degree of freedom. The pieces do not need to be glued together. They can somehow go in different directions. And the carrot use this additional degree of freedom to release some tension, some energy, which we now discover after the experiment that, in fact, there was such stress. There was such a potential energy that could be released. Okay, so, and I mean, this is in some sense a funny example, but it's in some sense a toy example of a serious phenomena occurring in various contexts. And there is a slightly generalized paradigm to model such phenomena, which is called sometimes incompatible elasticity or non-Euclidean elasticity. So in this framework, an elastic body is no longer a subset of Euclidean space. Instead, it is a compact-oriented Riemannian manifold with boundary. And let's say that G is the metric, and we call G the reference metric. So instead of having a reference configuration, so the body doesn't come with a preferred way of lying in Euclidean space, instead of a reference configuration, we now have a reference metric, which in some sense encodes the local distances, the ideal distances between the molecules in the body, in some sense. Okay, this is a continuous model, of course, but there are discrete analogs, but we want to get to them today. So we think about the metric as the fundamental geometric object, which encodes, in some sense, the mechanics of the body. And again, elastic energy is a function of the space of configurations. Well, still partially classically, the configurations are just mappings of the manifold M into RD. And again, the dimension of the manifold is D, and the ambient space is also D-dimensional. So there is no codimension. The codimension here is zero. Okay, we don't embed some low-dimensional object in a high-dimensional object, but the dimension of the source space and the target space are the same. So this is bulk elasticity, and not elasticity of thin bodies, let's say. Okay, and so the energy is again some kind of, if we are looking at the typical prototypical energy from before, the energy is again an integral of the distance of the map from being an isometric immersion. So there is a natural way to define this distance in an analogous way to how it is defined in Euclidean space. I mean, essentially, once you represent everything in autonomous frames, then you just recover the standard distance of a matrix from SO. So you can generalize the definition quite easily. And but you know, need to be careful with the details. But essentially, there's nothing complicated here. And one can generalize this setting even further and replace RD also with another ambient, with another manifold, Riemannian manifold, D-dimensional Riemannian manifold, which does not have to be Euclidean space. So you can embed one curved space in another curved space, essentially. And now the elastic problem is finding energy minimizing configurations, as before, from M to N. But now, even when we do not put any additional constraints, we can recover and get a non-trivial problem. For instance, if M has non-zero curvature, if the metric on M is not flat, and the target space N is just Euclidean space RD, then of course, we won't have an isometric immersion from a curved manifold into flat space of the same dimension. So any map will have a positive energy. It won't be an isometric immersion. I mean, a map has, I didn't say it, a map has zero energy, even only if it's a weak or I don't know, smooth, depends on the regularity, even only if it's an isometric immersion. So if the source manifold is non-flat and the target manifold is flat, we do not have isometric immersions. So any map will have a strictly positive energy. And in fact, one can prove that the infinite energy will also be positive. So we already get a non-trivial problem, even if we do not add any additional constraints, let's say on the boundary values of the map. So this is the basic problem in this framework. And in this talk today, I want to focus on a very specific sub-problem, which considers what happens when we squeeze. So now we want to embed our body M in a target space N, which has smaller volume. So we force the body to squeeze in some sense, and we ask how to squeeze this body inside the target space with minimal distortion. So to get more specific, we'll focus only on 2 dimensions here. So the main result I'm presenting today is the following. If M and N are compact surfaces, and P is some exponent greater or equal than 2, then let U be any Lipschitz configuration, any Lipschitz map, which is injective and having non-negative Jacobian. Then the P elastic energy, where P plays the role of the exponent, is greater or equal than some explicitly given function f raised to the power P over 2, evaluated on the ratio of areas. Vm and Vm are the areas of the source surface and the target surface. And f is explicitly given below. We'll in a second discuss it a bit more. So I just want to say for now that in some sense this statement is kind of crude because it only uses it gives a lower bound which uses in some sense very little information. It only uses the discrepancy between the areas of the source manifold and the target manifold. I mean, it doesn't use any other information. Of course, the metric contains much more information than just the area. So in some sense, it looks very crude, but we'll see that it still can lead to non-trivial phenomena and observations in relevant cases. Okay, so again, this is again the low bound stated. The P energy is greater or equal than F raised to the power P over 2. And F is explicitly given here. And I want to note a few things. So first, it turns out that F is a C1. This is, you can just check it easily. And it's monotonically decreasing and convex. So the monotonicity is quite natural here because the more, so as we said, sorry, just a second, something. Yeah, okay. So as I said, the area of the target is smaller than the area of the source object. So we squeeze. And naturally, we expect that the less we squeeze, that is, as the ratio of areas gets closer to 1, we can say less in general about bounding the energy in terms of the area discrepancy. I mean, in the limiting case where the area of n equals the area of m, we cannot say anything in terms of the areas ratio. We can just take m equals n and just takes the identity map and it has 0 energy, so we don't get any bound. And naturally, the more we squeeze, the more the ratio of areas gets smaller, then the lower bound gets higher, right? Because we expect that the more we squeeze, the more distortion we must pay. So F is monotone. This is not surprising. And what is non-trivial in advance is that it's actually convex. This will be important later. And in fact, it's the restriction of F to the interval 0 up to quarter is affine. And after quarter, it becomes strictly convex. And this will also be important later. So this is our function F. Okay, so let's get back to the statement. So again, we have 2 surfaces and we have a map, a configuration, a mapping, a Lipschitz map, which is injective and have non-negative Jacobian. Then the elastic energy is greater or equal than this function evaluated in the ratio of areas. And now we want to understand, okay, this is some lower bound, but we want to understand when is it attained? I mean, is it trivial, non-trivial, what can happen? So this will be naturally phrased in terms of the singular values of our map, or of the differential, of the formation gradient, du, W, whatever you want to call it. So here's the characterization. If the ratio of areas is greater or equal than quarter, then it turns out that the lower bound is becoming an equality. The inequality is becoming an equality if and only if U is a bijective homothety. And by homothety, I just mean a scaled isometry. In other words, a homothety is just to fix the terminology here. A homothety is a conformal map with a constant conformal factor. So it has a constant Jacobian. In other words, it's just in some sense a scaled isometry. So if the ratio of areas is greater or equal than a quarter, then the homotheties are the only maps which attain this bound. And we have some kind of a phase transition when we shrink by more than 4 times the area. When the ratio of areas is less than quarter, then there is some splitting here in terms of the exponent. If the exponent p equals 2, then equality holds if and only if the sum of singular values are 1, almost everywhere. And when the ratio of areas is less than quarter and the exponent is strictly greater than 2, then the maps U which attain the inequality satisfy that the sum of singular values is constant 1, and also the product of the singular values, the Jacobian, is also constant and must equal the ratio of areas. In other words, these are maps that have constant sum and constant product of singular values, so they just have constant singular values almost everywhere. So this is the characterization of the mappings attaining this bound. And naturally, if you fix M and N, whenever the bound is attained, you get a minimizer. Okay, so this is a way of establishing, of demonstrating existence of minimizers. If you can construct such a map with these properties that attains the bound. I see there is a question in the chat, maybe. Link to paper. Okay, thank you. Okay, if there are any questions, so feel free to stop me. Okay, sorry. Something. Yeah. Okay. Okay. So now I want to focus on a specific case where I assume that M and N are homothetic. In other words, the target space N is just a smaller shrinked copy of the source space M. So N is just a shrink version of M. And our statement from before was that if the ratio of areas, which is lambda squared, is greater or equal than quarter, okay, sorry, I forgot to say. So for homothetic manifolds, we always have natural candidates for minimizers, which are the homotheties. We have canonical maps, the homotheties, which we can ask, do they minimize the energy? So when the ratio of areas is greater than or equal to quarter, then the homotheties are the unique minimizers. So the optimal way in terms of distortion to shrink M into a scaled shrink copy of itself is just to take the uniform shrinkage up to a composition with isometry. And the interesting question, of course, is what happens when the ratio of areas is less than quarter. Are homotheties still minimizers? Do they remain minimizers? And I wrote that the answer is not necessarily, but in fact, it turns out that there's a stronger statement which is true. And if you want minimizers of Lipschitz regularity, then the homotheties are never minimizers. When the ratio of areas is less than quarter, it doesn't matter with what kind of shape you have, if it's some shape in the Euclidean plane, so any, I don't know, strange shape in the plane, you can lower the energy below what homotheties can give you. And for start, we'll demonstrate this for disks. So here's the proposition. Take the disk, let's say without the origin. I mean, the point of removing the origin is that for a moment I want to focus on smooth diffeomorphisms, and there is some singularity on the origin that we'll see later. So if you have the disk without the origin, say, so this is the source manifold M, just the Euclidean disk, and N is a shrinked copy of the disk. Then I claim that the minimum of the energy is realized by a smooth diffeomorphism. So let's see what we are looking for. I mean, we search for maps from D to lambda D, and by the characterization given by the theorem, we want maps which has sum of singular values 1 and product lambda squared. By the way, this is, I forgot to mention before that there is a relation here between the fact that the singular values have constant sum 1 and the fact that the phase transition, which is stated here, occurs at a ratio of areas a quarter. And the relation is, of course, the arithmetic geometric inequality. Okay, I didn't say it. So it's not a coincidence. So anyway, we look for maps from D to lambda D, whose sum of singular values is 1, and their product is also constant and equals lambda squared, at least in the generic case when the exponent is greater than 2. And now we can compose this map with 1 over lambda, so we can scale. And equivalently, we are looking now for maps from the unit disk into itself, which has constant sum of singular values 1 over lambda, and the product of singular values is 1. But product of singular values 1 means that these are area-preserving maps. So we are looking for area-preserving diffeomorphisms of the disk, which have constant, distinct singular values. And they're distinct because if sigma 1 equals sigma 2, and it's an area-preserving map, so the product is 1, then sigma 1 equals sigma 2 equals 1, and then this map will be in isometry, and the sum of singular values will be 2, and this means that lambda here will be 1/2, and lambda squared will be 1/4, and we shrink by more than 4 times, right? I mean, we now assume that we're in the non-trivial regime when the ratio of areas is strictly smaller than 1/4. Okay, so we are looking for so to focus, we're looking for area-preserving diffeomorphisms of the disk, which has a special property. They have constant distinct singular values, sigma 1, sigma 2, which the value of sigma 1, sigma 2 is determined by lambda, by the amount we wanted to shrink, the non-scale problem. So now we can see why this is not trivial a priori, because of course the linear map, the affine maps, doesn't work because it turns the disk onto an ellipse. It goes outside, gets outside of the disk. So we must look for nonlinear maps. In some sense, the problem with the affine map is that it always distorts the same direction by the same amount, right? By sigma 2, let's say by the largest singular value. So in some sense, we need to look for a map whose singular vectors are rotating. So we want to push the same direction more and more and eventually get out of the disk. So we need some kind of twisting. And here is an example of such a family. So what do we have here? So for now, think of t as being a fixed parameter. I mean, t depends on lambda via some dependence, but t is a parameter depending on lambda. So let's say lambda is fixed. We want to shrink the disk onto a scaled version of it, a scale lambda where lambda is a fixed scaling ratio. So t is also fixed. So ut is a map from the disk onto itself. And what does it do? It maps a concentric circle, each concentric circle onto itself isometrically and keeps the orientation. But each circle gets mapped onto itself with a phase, which depends on the radius. So if you think what happens to a specific ray, it gets distorted to a curved ray, as you can see in the picture right here. This is when t equals 0, we just have the identity map. And this is the picture of how these pizza slices are distorted when t equals 1/2. And actually, when you let t flow with the time, then it's easy to see that ut is just the flow of the divergence-free vector field log r partial theta. So this immediately shows that ut is an area-preserving map for each t, and I claim that it has constant singular values. This can be easily checked. And I want just to maybe show how this is how the twisting looks. So we started with t0, the standard disk, and we twist it as t grows. And now remember that actually t depended on lambda, right? And when we shrink more and more, when lambda tends to 0, t tends to infinity, which means that when we want to shrink the disk more and more, we need to twist more and more. And if you also account for the connection between the amount of shrinkage and the amount of twisting, which depends on t, then you get the following. So this is actually how the optimal map looks like. So we start the optimal shrinkage. You start with the disk, and up to some time, until the area gets 4 times smaller, you just take the uniform shrinkage. And after this time, when you shrink more and more, you twist more and more. Okay, this is what is happening in the animation. And when you shrink into a point, then the twisting becomes infinite. Okay. So yeah, okay, just know that this problem in dimension 2, actually, it was from advanced, it had an inverse invariance symmetry, because we were looking for R representative diffeomorphisms having fixed singular values sigma 1, sigma 2. And if U is such a map, then U inverse will also be, of course, R preserving and have the same singular values in dimension 2. So the problem is inverse invariant, and in this case, in this family, for each ratio of shrinkage, the family UT gives us two choices of maps, UT and U minus T. And again, here in this example, UT is a flow, so of course U minus T is the inverse of UT, and it just means that we can in some sense there is a symmetry breaking here, right? I mean, we started with uniform shrinkage, and now we need to break the symmetry. We cannot continue to using a uniform shrinkage, and we need to decide if we want to go clockwise or counterclockwise, right? So this is the two choices here. And again, I'm not saying, and in fact, it's not true that these are the unique minimizers. This is just an example. Okay, the minimizers are in general are far from being unique, but it's an example of a non-trivial family of minimizers. Okay, so this finishes these examples. Maybe I'll say a few words again on the topological nature here. So in some sense, so this particular family, each UT is a Sobolev map. It's smooth on the disk without the origin, but it's not smooth at the origin. And by interpolating between the logarithmic phase and the constant phase, which just means a rotation, you can actually easily deduce that the infimum value of the energy over all the diffeomorphisms of the complete disk is the same with or without the hole. But now the question, is it attained? So can we actually construct an area preserving diffeomorphism, smooth diffeomorphism of the complete disk with the origin? So I don't know the answer to this question, actually. It's as far as I could figure out, I haven't found in the literature any such claim. There is a conjecture, I think, but I didn't find any answer. But at least for the special case of P equals 2, we need something less restrictive. So, and we can, in fact, realize this bound by an infinite dimensional family of energy minimizing diffeomorphisms. I'll just give a brief description of this. So we consider now a slightly more generalized kind of map. So R theta goes to psi R theta plus H of R. So each circle of radius R gets mapped onto a circle of radius psi R, and with the phase depending on R. But now psi is not the identity, it's not linear. And psi and H needs to satisfy some relation, some OD. And actually, you can construct this where this psi starts from being linear. So at the beginning, you do start with a rotation, but at some point, so you start with a rotation up to a small radius, so you don't get any singularity at the origin, and up to some point you do something which is less trivial. And okay, where did I get this from? So recall that there was a difference in the characterization of the minimizers between the P equals 2 and P greater than 2. When P equals 2, U satisfies, has an energy which is identical to the lower bound, if and only if its sum of singular values equals 1. And for P greater than 2, equality holds if and only if the sum of singular values is 1, and the product is also constant, which equals the ratio of areas, which is lambda squared. So for P equals 2, we do not have any constraint on the Jacobian, only on the, at least not any pointwise constraint on the Jacobian. Of course, the integral is the ratio of areas, but only constraint on the sum of singular values. And when you consider maps of the above form, you can just check, compute, and see that the condition of the singular values translates to the ODE, the coupled ODE I described there before. So you look for such a losange, And if you try to use these kind of maps to construct smooth solutions for p greater than 2, so with constant Jacobian, then the only solution of this equation gets you back to the logarithmic spiral we saw before, which is not smooth in the origin. So you don't get anything more out of it, if you try to construct such maps for p greater than 2, which has constant singular values. So for p equals 2, we construct maps which do not have constant singular values. Only the sum is constant. This is the point. Okay, and maybe before I continue, I'll just say that I showed this for disks, but actually, I mean, if we are satisfied with, let's say, Lipschitz regularity, then one can in fact construct such maps from a square onto a smaller scale copy of a square, and since you can essentially tile any reasonable shape in the plane by a union of squares, and you can glue these maps, then actually you can build minimizers for any kind of shape in the plane. So you can shrink any map in the plane in this non-trivial regime onto a shrinked copy of itself. So it's not just for disk true, you can lower the energy for any reasonable shape. And in fact, the construction for the square is in some sense a discrete analog or a squared analog of this radially symmetric construction of the disk problem. Okay, I want to say something about the proof sketch. So let's consider the pointwise problem. So forget manifolds, surfaces. We're just looking about the pointwise matrix calculus, I don't know, textbook. And my claim is the following. For any matrix, 2x2 matrix, with a positive determinant, the square distance of the matrix from SO2 is greater or equal than the function f from before, the lower bound, evaluated at the determinant of A, which is given here. Let me just jump a little. In other words, I'm trying to solve the following problem. Inside the class of all matrices of determinant S, so the matrix A induces volume distortion of S, and inside this class, we are looking to minimize the distortion from SO2. And it turns out that this function is the f I described before, and I will show it, tell something about it in a second. And it turns out that for this pointwise problem, you have an equality. So the distance of A from SO2 is greater or equal than f of the determinant of A. And if the determinant of A is greater or equal than quarter, then equality holds if and only if A is the conformal matrix. So sigma 1 equals sigma 2. And when the determinant is less than a quarter, then equality holds if and only if the sum of sigma values is 1. Okay, so now I want us to have intuition for why there is a phase transition. Okay, why we expect a phase transition here when the ratio of errors becomes sufficiently small. And so this problem is of course by SO invariant, and in terms of singular values, the determinant is just a product, sigma 1 equals sigma 1 sigma 2 equals S. So we want to minimize the following problem, which is written here, and the distance of the matrix A from SO2 is just the sum of squares of sigma 1 and sigma 2 minus 1 squared. Sigma 1 minus 1 squared plus sigma 2 minus 1 squared. This is just the distance of a matrix from SO2, the equivalent distance. So what happens here? So one natural guess is to, or you can always try to, to share the load here. I mean, we have a problem, right? We would like to choose sigma 1, sigma 2 equals 1. We can't do that because we have a fixed area distortion. So we need to somehow share the load of this distortion between sigma 1 and sigma 2. So a naive guess would just be to try uniform sharing of the load. So to choose sigma 1 equals sigma 2 equals square root of S. And this indeed gives the optimal, the optimal point when S is small. I mean, let's think of this geometrically. We are looking on the graph of sigma 1 sigma 2 equals S, and we look for the closest point on this graph to the point 1, 1. So when S is sufficiently close to 1, then indeed the uniform load is optimal. But let's say in the limiting case, when S gets very close to 0, it's not. And you can see this here in this animation, so what happens here is that we started with s equals 1, and the closest point on the graph is uniform, and at some point it gets split. On some point, from a certain point, it stops being a global minimizer. In fact, it becomes a local maximizer, and the minimizers split to 2 different points. I mean, of course, we have a mirror points here because the problem is invariant under replacing under commuting of sigma 1 and sigma 2. And actually, when you take s to be 0, this is immediate. I mean, for s being 0 or very close to 0, then if you take the uniform sharing of the load, you get penalty of 1 and 1 on both of them. And if you take just one of them to be single values, one of the single values to be 1 or very close to 1, and the other to be very small, then you get penalty of almost just 1 and not twice 1. So this is the source of the phase transition. You can already see it in the pointwise setting. So it doesn't really, it's not really connected to the manifold nature of the problem. Okay, so this was the intuition for why we expect a phase transition for the bound. And now I will continue with the sketch. So let's say that p equals 2 for simplicity. And again, we have an injective Lipschitz map from M to N, non-negative Jacobian. We want to prove that the elastic energy, the integral over the square distance from SO, is greater or equal than F evaluated and the ratio of areas. So the energy is just what I just said. And equality 1 is just by definition, that's how we defined F, right? So we can use the distance from SO is bounded below by the function F evaluated at the Jacobian. And inequality 2 is the Jensen inequality. Here we use the fact that F is convex that I said at the beginning. And now the area formula, we have that the integral of the Jacobian is the volume of the image. So we get that the energy is greater or equal than F evaluated and the ratio of areas between the image and the source. And the last inequality is due to monotonicity. I mean, we are squeezing here. So if we use the entire area given to us, we just improve the result. And I just want to say that I said before that F is convex, and it's in fact affine from 0 up to quarter, and after quarter it's strictly convex. So this also of course plays a role. When you try to characterize when equality occurs, you just go and trace back all the inequalities, and so there is a difference in the Jensen inequality here between the cases when the ratio of areas is greater than quarter or less than quarter. This is the reason why when the ratio of areas is less than quarter, you can have, when p equals 2, you can have freedom in the values the Jacobian takes. It doesn't need to be constant because the Jensen inequality becomes trivial because you are in the branch where you are in the domain where F is affine. Inequality 1 becomes an equality. This is just a pointwise problem we discussed before. I mean, we know that happens when the gradient is conformal or the sum of singular values is 1. So this is basically the proof. And when p is greater than 2, you just repeat the same argument or use another one more time Jensen inequality. At some point, it's essentially the same. Okay, so this is the end of the proof sketch. I have 5-10 more minutes, right?
Yes. Take
okay, great. So I want to talk a bit about stability. So up to now, we talked about exact minimizers, right? So here's the statement. So I'm restricting everything now not to general surfaces, but domains which are Euclidean domains, open subsets, let's say with Lipschitz boundary in Euclidean space, in the Euclidean plane, sorry. And I assume that the ratio of areas, again, less than 1 because we squeeze, and it's strictly greater than quarter. So we are strictly inside a regime where the maps which attain the lower bound are homotheties. And assume that there is a sequence of Lipschitz injective maps that satisfy that their energy, the elastic energy, converges to the lower bound. So we know that if we have a map whose energy exactly equals the lower bound, this map must be a homothetic, because this is the regime of the areas, the volume areas, the volume ratios. Sorry. So if U has an energy which equals the lower bound, it must be a homothety. And now we have a sequence whose energy converges to the lower bound. And the statement is that UN has a subsequence. This is the stability result. UN has a subsequence converging strongly in W12 to a C infinity surjective homothety, which has constant Jacobian, which equals the ratio of areas. And it's injective on the interior on omega-1, and it's injective almost everywhere in the sense of inverse images on the image. And if you add some topological assumptions like that the maps UN preserve the boundaries, then in fact the limiting map is a bijective diffeomorphism. And note that in this statement we didn't a priori assumed that omega-1, omega-2 are homothetic. This is a conclusion. So if you have two domains and someone tells you that you can realize by infimum the energy, you can get closer as you want to the value of the energy given by the lower bound, then in fact the domains were homothetic to begin with, because the limiting map is a homothety. And I think that this statement deserves a context. Let's perhaps state a similar classic result, which in some sense is similar. So this is a classic result of Riemannian, which says that in any dimension, in any exponent p, you have a sequence of maps between omega and RD, whose elastic energy distortion tends to 0. Then there exists a sequence which converges to smooth isometry. So if you get closer and closer to having a 0 distortion, then you need to converge to isometry. In other words, if your energy gets closer to the energy, if your energy converges to the energy of an isometry, you have a subsequence converging to an isometry. And the statement I showed before was an analogous statement, which says that when the energy gets converges to the energy of a homothety, then the sequence must converge up to a subsequence to a homothety. And this statement actually has been generalized to maps between manifolds by Paxad, and later when the target space was also a Riemannian by Raz Cooperman, Simao, and myself. Sorry, by Paxad and Marta Levitska. Sorry. Okay, so this was generalized anyway, and to manifolds. And okay, so I just want to say, okay, so a key component in the proof sketch of the stability result. So again, this is the statement. The energy converges, then there is a subsequence converging to a homothety. And the key step is that, okay, usually you use some weak compactness principles, and you get, of course, a subsequence which converges weakly to some map. And we have what's classically known as the higher integrability properties of determinants or Jacobians, the weak continuity of Jacobians, right? That if U1 weakly converges to U in W12, then the Jacobians weakly converge in L1 for any compactly contained subset. And the point here is that this key step doesn't hold as is between manifolds. For example, if you take the two-dimensional sphere, then you can construct a sequence of smooth conformal diffeomorphisms. So the best thing you can hope, smooth conformal diffeomorphisms, which weakly converges to a point, to a constant map. So the Jacobians do not converge to 0. You can do this very easily by using the stereographic projection. You map the sphere to the plane with the stereographic projection, and you dilate more and more in the plane, and then you translate back to the sphere, and you actually push more and more parts of the sphere into a smaller area around the North Pole, and eventually in the limit everything gets pushed to the North Pole, and you get a sequence which converges to a point. So as I stated, it doesn't hold, and there are generalizations of this statement which are phrased in geometric measure theory frameworks, but essentially, I'm quite convinced that this is essentially the only or key component missing for advancing the stability result beyond Euclidean domains. Okay, so this missing step is the reason that I stated my result only for Euclidean domains, but the rest of the proof essentially goes verbatim for Riemannian in Riemannian context. I'll just say that proving stability for exponents greater than 2 should be much easier because then the weak convergence hold. I mean, the problem with p equals 2, of course, is that this is the critical dimension, right? P equals 2 equals the dimension, so this is why everything gets a bit harder. Okay, so this is what I want to say about the stability. So just before I'm going to do open questions. Okay. Last thing I will say that I did not elaborate in this talk is that interesting fact. You can so this entire talk I only talked about the Euclidean energy density, right? We have fixed energy density W, right? The distance from metrics from SO. I mean, I'm referring to the W right in the beginning of the talk. The W here. We had the fixed energy density, and everything was about this specific problem. But actually, you can prove that for any bi-SO invariant energy density, that you want to choose, then for a short amount of shrinkage, the homotheties will be the best candidates. So if you shrink by a little, homotheties will be the energy minimizers, no matter which energy you choose. This is a generic, completely generic phenomena. And in fact, for some energy, and we demonstrate that for this energy density, the homotheties do not remain minimizers always. Once you shrink by more than a quarter, they are not minimizers anymore. But there are energy densities, and I characterized some partial families of these. There are energy densities where the homotheties remain minimizers no matter how much you shrink. So the fact that the homotheties remain or do not remain the optimal way to shrink a body into a scaled copy of itself depends on the energy density you choose. Okay, I mean the homotheties always, there is some kind of stability. The homotheties always start being minimizers, but if you want to know if they continue being minimizers when we shrink by very much, then this depends on the energy density. Okay, so I think that I'm basically finished. I'll just mention some open questions. Okay, so in this specific talk, I discussed only. I have assumed that the exponent p is between 1 and 2, and sorry, it's greater or equal than 2. Sorry, and an initial question is what happens when p is greater than equal than 1, slightly smaller than 2. And the problem is that you can try to repeat the proof, but f raised to the power of 2 over 2 is no longer convex, so we actually need to use the convex envelope of f. But then some other things get a bit more trickier. So, but you can obtain full characterization, and in fact, it's very interesting because you get a regularity change because the maps which attain the bound in this case cannot be smooth because the Jacobian needs to switch between two different values. Again, this is related to the way that you want to realize the convex envelope by some kind of a combination. So things get a bit trickier and in some sense, I think even more interesting. Okay, so just a funny question is that I still don't know, I mean, if there are energy minimizing diffeomorphisms between complete disks for p strictly greater than 2. And I'll just remind you that this is equivalent to asking, take the complete disk, is there an area preserving diffeomorphisms having fixed constant singular values, given sigma 1, sigma 2, which does not have any singularity, so I don't know. I will say that the regularity does matter here in some sense, because let's say that you leave the Euclidean world and you want to focus on, ask this question about general topological surface, and you look for any surface with a Riemannian metric, and you look for area preserving diffeomorphisms which have constant singular values, then most surfaces won't have this. Only the torus can admit such things, because if you have constant singular values, this means that the tangent bundle splits into a sum of two line bundles, because the line bundles correspond to the singular vectors. I mean, at each point you have the direction which gets stretched by sigma 1, and the other vector which gets stretched by sigma 2. And locally you can choose, since the singular values are distinct, you can choose these singular vectors in a smooth manner locally. So anyway, the tangent bundle splits, and this means that in the boundaryless case, in the closed case, the only such surface is the torus. So this means that at least for other surfaces, you do not have smooth R-representative diffeomorphisms with distinct single values. Of course, it doesn't rule out the existence of such Lipschitz diffeomorphisms, for such Lipschitz projections or something, because then the topological argument breaks down. But just an interesting point. And okay, I think it's very interesting to try to generalize the stability result to manifolds. Again, as I said, the missing component is a very interesting phenomenon of concentration of volume between manifolds. And of course, you can generalize everything to higher dimensions, etc., etc. Okay, I think I finished now. Thank you very much for the attention.
Thank you. Come on.